Hello, everyone. My name is Michelle Larsosa, and my presentation for ECE 560 is on Programmable Logic Controllers, also known as PLCs. PLCs are able to receive data through its inputs and send operating instructions to its outputs. They control a system's functions using the internal logic programmed into it. PLCs were first developed in 1968 by a group of engineers at General Motors based off of specifications for a standard machine controller. And the purpose of these machine controllers was to help control the manufacturing processes to make them more efficient in running a auto plant. For the elements of the specifications, it took into consideration the use of solid state components that were both modular and expandable. They contained 16 units that could be expanded to 256. They had 16 outputs that could be expanded to 128. They were easy to program and reprogram, and they would not lose any of their stored programs in the event of a power outage. So for the purposes of my research, with it being focused on PLCs within manufacturing settings, these are closed loop systems. And so examples of open loop systems would be like handheld devices that you can turn on and off like a hair dryer. So for closed loop systems, they're not that simple. They're a little more complex, but the purpose of them is to be automated so that they can run by themselves. So that they're not manual, they are automated and can function with minimal to no direct supervision. And some of those advantages are the high accuracy due to its measurability, making it more stable and efficient. And then the disadvantages would be the initial high cost in setting up and then ongoing around the clock maintenance. The main components of a PLC are the power supply, the input module, output module, and the central processing unit, also known as the CPU, and memory. The power supply provides power to the PLC. It energizes it. It also converts the input source power into signal level voltage that's used by the processor and other modules so that they can work in sync with each other. They can also come in different sizes and power ratings depending on the type of PLC that's being used. The common output voltage is 24 volts DC, and the common current ratings are 2 to 10 amps for smaller systems and up to 50 amps for larger systems. The input module detects the status of input signals like the push buttons, switches, and temperature sensors. It receives signals from switches or sensors and sends them to the processor for further evaluation. And they can be discrete or analogous, that's digital or continuous. And then they can also be converted back and forth depending on how the program is set up. The output module controls the devices such as relays, motor starters, and lights, and is divided into 3 types depending on the type of output that's required. So there's relay output, transistor output, or triac output. And the triac is capable of controlling AC loads, where the transistor output module they only control DC loads. So again, this is based off of the type of output that's intended for the system. The central processing unit is like the brain of the PLC, much like it being the brain of a computer. It runs lateral logic routines that help to automate the factory processes. It also processes data and computations by accepting inputs and then produces the appropriate outputs. The memory included has both ROM and RAM memories. So the ROM contains the operating system, the driver, and the application programs. And then the RAM stores the user written programs and working data. Ladder logic, which is heavily used for PLC programming. It's a graphic user interface where the user can just drag and drop the graphic interface to help program the PLC. The programming language resembles an electric schematic drawing, where you can see like where switches and relays are laid out on a schematic. That's what you would see in a ladder logic program. It's easy to troubleshoot the programming code because you can see the logic flow from left to right. And here's an example of ladder logic for a motor starter. So you have the relays here. And again, you have the start and stop, and you would read it going left to right. Also, taking into consideration to help increase the controllability and stability of a PLC is the use of linear quadratic regulators and Gaussian design when developing a PLC. So the LQR and LQG, they help to obtain optimal gains that yield more stable and controlled responses as opposed to trial and error. So the LQR and LQG design helps to reinforce the idea of stability for your PLC program system. In a normal LQR, the regulators are desired at a zero state. In real life, real world situations, zero state is not always available to us. And so again, that leads us into taking into account any type of noise and disturbances in a system. So then the Kalman filter is used as an observer to help estimate the system states. And again, to provide even more reliable stability in its design. And here we have an example of the type of decision-making and development when designing in LQR and LQG for the PLCs. So there are decisions that have to be made and in the designs. And so these are the examples of that here. And in the LQG, we have the implementation of the Kalman filter that helps to control a system, taking into account any type of noise and disturbances that might be present within it. So the overall advantages and disadvantages for a PLC. For the advantages, it has a very fast scan time, great computational capabilities. It's easily programmed and highly reliable. And so that's the goal when implementing a PLC within a closed loop system or even open loop. But again, these advantages are necessary when designing high-level closed loop automated systems. For the disadvantages, it's mainly with downtime being uncertain. So that has to be taken into account that if there's anything outside of routine maintenance, if there's any type of major troubleshooting that has to go on or any repairs, the PLC can't control, what repairs may need to take place. And so any type of high temperature or high vibrational conditions that might be outside of the norm in that system have to be taken into consideration as well when trying to anticipate any downtime for a system. Here, I just want to give acknowledgement to some of the references that I use. We have library automation direct, the Polytechnic Hub, also instrumentationblog.com, ACC Automation, and Ladder Logic World. And then also want to give acknowledgement to the PLC manufacturers that are in existence. These are some of the most popular ones that are out on the market today and that you might find inside of an auto plant in particular. Allen Bradley is a very popular one that's used in most auto manufacturing facilities. Then you have Siemens, ABB, and Honeywell. And also we have Panasonic and Hitachi. Right now, this concludes my presentation. I thank you so much. And if there are any questions, please reach out to me and let me know if you would like to discuss anything further. I would also like to thank Professor Farouk and the University of Michigan Dearborn for their ongoing guidance and assistance in helping me with my research in this project. And I just thank them and everyone else for their time.